An electric field, like a gravitational field, completely fills the space surrounding the charged object that causes it, behaving like a messenger that signals to all other charged particles in space, "Hey, I'm here. I'm a charged particle." This message, like all messages, must travel at a finite speed. The speed at which the electric field message is sent out is the speed of light. So if I snap my fingers and a positive charge appeared right there, that message will start to spread out, and it takes time. And the speed in which that message spreads out is the speed of light. Speed of light is insanely large. It is 3 times 10 to the 8th meters per second. To put that into perspective, that means a beam of light could cross a distance of about a football field in 3 microseconds. That's 3 millionths of a second. A beam of light could circle the Earth a little more than 7 times in about a second. It takes only a second and a half for a beam of light to go from Earth to the moon. So light is insanely fast, and the electric field moves at that speed, the speed of light. Once the electric field message is sent out, it will exert a force on another charged particle in space around it. But I have to tell you, if there are no other charged particles in space, how I have this drawn with these concentric circles, that's not how we really map the electric fields. I'm using these circles as an analogy, or the analogy I'm using with these circles is kind of like sound waves. You yell out and the message goes out. Or you could visualize it as maybe you drop a rock in a lake and ripples spread out. But this isn't really how you and I will model the electric field, because it doesn't really look like this. Instead, we're going to use electric field lines to help us visualize the electric field of a charged particle without using any or much mathematics at all. Let's start with these 2 charges, a positive and a negative charge. The electric field points outward for all positive charges, and it points inward for all negative charges. The electric field for positive charges points outward radially away from the positive charge in the absence of any other charged particle. Also, in the absence of any other charged particle, a negative charge's electric field will point inward. So the field lines for positive charges will always begin on a positive charge and point away, while the electric field lines for negative charges will always end on the charge pointing towards it. If you want to know how to determine the direction of a charge's electric field, the direction of a charge's electric field is the direction of the force that that particle would exert on your test charge. Let's see if we could get a sense for the electric field due to this positive charge. If you probe enough points in space, you will be able to create a picture of the electric field due to that source charge. We know the electric field points radially away because we know the electric force of repulsion against our positive test charge lies along the same line as the electric force. That took me several seconds to draw. And that obviously takes a very long time if we want to just simply represent the electric field of a charged object. So instead of drawing thousands of individual vectors, we've created the model of electric field lines. The electric field then can be represented by radial lines emanating from positive charges these lines I'm drawing, these electric field lines, indicate the direction of the electric field at any point. That's indicated by the arrows. For negative charges, we could simply model the electric field due to negative charges as these lines. And the direction of the electric field is radially towards that negative charge. So again, how do we know the direction of an electric field? We place a positive test charge in space. We observe the direction of the electric force acting on our positive test charge in space. And the direction of the electric force on our positive test charge is the same direction as the electric field on our positive test charge.